Today we're going to continue looking at the definite integral. If you would recall, we looked at this example last week where we're using the fundamental theorem of calculus to evaluate the definite integral from 0 to 2 of x squared minus 4 dx. We found the antiderivative, 1/3 x cubed minus 4x, and then evaluated at 2 and 0 and subtracted. So here, little f is the x squared minus 4. That's the function that we're integrating. And capital F, an antiderivative of little f, is 1/3 x cubed minus 4x. We evaluate an antiderivative at the endpoints. So here we have capital F at B minus capital F at A. And that's where we came up with the negative 16/3. So some things that we recognize about from this problem. This function, x squared minus 4, was negative on the interval from 0 to 2. So when the definite integral was calculated, we got a negative 16/3. The area bounded by the graph of the function, the x-axis and the y-axis, is 16/3, but the definite integral will report that as negative. So today, we want to look at what happens if we have a function that changes sign on the interval over which we are integrating. So let's calculate this same function, but instead of going from 0 to 2, let's go from 2 to 5 of x squared minus 4 dx. Since we're using the same function, x squared minus 4, in our integral, we can use the same antiderivative, 1/3 x cubed minus 4x, but this time we'll evaluate from 2 to 5. So I'll do 1/3 of 5 cubed minus 4 times 5 minus 1/3 of 2 cubed minus 4 times 2. So here we're going to have 125/3 minus 20, and then minus 8/3 and plus 8. Since we have two terms in our antiderivative, we have to make sure we use parentheses. We subtract the first term, but we're subtracting a negative for the 4 times 2, so it'll be a positive 8. So don't forget your distributive property. 125/3 minus 8/3, that's going to give us 117/3. And then minus 20 plus 8 is going to be a minus 12. 12 is 36/3. So we get 117 minus 36. So it's too Monday for me to do arithmetic. So 117 minus 36. I thought I was going to be fine, but I'm clearly not. 81. And so we get 27. So in this situation, we're looking at an area, but on the interval from 2 to 5, the function x squared minus 4 is above the x-axis. So here, the area under the graph of x squared minus 4 and above the interval from 2 to 5 on the x-axis, the function is above the x-axis. And so that area is 27, and the definite integral is calling it 27. Calling it positive 27 because the area is, the function is above the x-axis. Next, what we should look at is what happens if I combine these two definite integrals into one definite integral and integrate from 0 to 5 the function x squared minus 4 dx. So we're going to use the same antiderivative, 1/3 x cubed minus 4x, but this time we'll be evaluating from 0 to 5. So we'll have 1/3 of 5 cubed minus 4 times 5 minus 1/3 of 0 cubed minus 4 times 0. So we get the first couple of terms from our previous integral. We get 125 over 3 minus 20, and then the rest is all 0. So 125 over 3 minus 60 over 3 is going to be 65 over 3. And this is a combination of the previous two integrals. If we take 27, the positive area, and subtract 16 over 3, we end up with 65 over 3. So 25 minus 16/3 is 65/3. So what happens here is that when we integrate from 0 to 5, we have a definite integral from 0 to 2 of negative 16 over 3. And we have a definite integral from 2 to 5 of positive 65 over 3. Oh, sorry, 81 over 3, 27. If I add these two together, if we look at the integral from 0 to 5, we see that the integral from 0 to 5 of x squared minus 4 dx is the integral from 0 to 2 plus the integral from 2 to 5. The definite integral counts area that's below the x-axis as negative. So this first term is negative 16 over 3, and the second term is 27. But if we add those together, we get the 65 over 3. If we wanted to calculate the total area, if I asked for the total area bounded by the graph of x squared minus 4 and the x-axis between x equals 0 and x equals 5, we would want to count the negative 16 over 3 as positive 16 over 3 in terms of area. So the total area we have would be 27 plus 16 over 3. That would be a slightly different question. So the total area is 16 over 3 and 27. So instead of subtracting, because the 16 is negative, I have 81 over 3 plus 16 over 3 for a total of 97 over 3. So 97 over 3 is the total area, but the definite integral gives 65 over 3 because it's counting the 16 over thirds area as negative because that area is below the x-axis. Any questions?
Yes, Professor Leach. On the last one, you wrote down total area. 16 over 3 plus 27 equal 97 over 3. What's the difference that and the 65 over 3 again? Can you please repeat that?
The 65 over 3 is the definite integral from 0 to 5. And when we calculate the definite integral from 0 to 5, the definite integral calls the area below the x-axis negative. So remember, the integral from 0 to 2 is negative 16 over 3. The area of that region is 16 over 3, but the definite integral is calling it negative because it's below the x-axis. So the definite integral is negative since the function is below the x-axis. So the area is 16 over 3, but the definite integral is negative 16 over 3. This is how the definite integral reads functions that are below the x-axis. It reads that area as negative. So the next question is, why does the definite integral read area below the x-axis as negative? And let's take a look again at the fundamental theorem of calculus. So the fundamental theorem of calculus says that the integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of little f. That is, capital F prime is little f. So when we look at little f, that's the derivative of big F. Notice that capital F at B minus capital F at A is the change in the antiderivative. So capital F at B minus capital F at A is how much the antiderivative changes. This is the change in capital F on the interval from A to B. So capital F at B minus capital F at A is the change in capital F on the interval from A to B. If we want to know how much a function changed, we look at on the interval from A to B, we look at the function f at A, that's where it starts, and find the difference between f at B, where it ends, and f at A, where it starts. It's the difference in the endpoints. That's how you find out how much the function has changed. So the other thing to notice is that little f is the derivative of big F. So since little f of x is the derivative of big F, if little f of x is negative, then big F of x is decreasing. If the derivative is negative, then the function is decreasing. If the derivative is negative, then the function is decreasing. And so now it makes sense that the definite integral is going to call area below the x-axis negative, is going to calculate that as negative area, because we're looking at the derivative of a function. And if the derivative is negative, the function is decreasing. So if we take another look at our function, so x squared minus 4, that's little f at x. And this is the derivative of big F. Since the derivative of big F is negative on the interval from 0 to 2, big F is decreasing. So big F prime is negative on the interval from 0 to 2. Therefore, big F is decreasing. And then the derivative f prime, big F prime, is positive on the interval from 2 to 5. So capital F is increasing. Since f is decreasing, capital F of 2 is less than capital F at 0. So capital F at 2 minus capital F at 0 will be negative. And since f is increasing on the interval from 2 to 5, capital F at 5 minus capital F at 2 will be positive, because that means capital F at 5 is greater than capital F at 2. And if capital F at 2 minus capital F at 0 is less than 0, that means capital F at 2 is less than capital F at 0. So this fits with what we looked at before about intervals where a function is increasing or decreasing. When the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. What we have added to that is that the area tells you the amount of increase and decrease. So we took what we previously know. If the derivative is negative, then the function is decreasing. The area tells you how much. of a decrease. If the derivative is positive, then the function is increasing, and the area tells you how much of an increase. Any questions? Take a look at another example. Let's consider the function sine x on the interval from 0 to 2 pi. Let's think about what this function looks like. So here's the function sine x. What we can see, based on the graph of sine x, we can see there's going to be some positive integral from 0 to pi and some negative integral from 0 to 2 pi, from pi to 2 pi. So we're going to have some positive area and some negative area canceling out. And what we know about the sine of x, these two areas are going to be the same. So we should expect the integral from 0 to 2 pi of sine x dx to be 0. Let's find out. The antiderivative of sine x is minus cosine x. Then we'll evaluate from 0 to 2 pi. So I'll have minus cosine of 2 pi minus a negative cosine of 0. Cosine of 2 pi is equal to 1. And cosine of 0 is equal to 1. So we get 0 as expected. Since the definite integral is counting the negative area against the positive area, and these two areas are the same, they cancel out to 0. So whatever area we had down here is the same as the area that we have above. The negative area cancels out the positive area. The negative area cancels out the positive area. We can see this if we evaluate from 0 to pi and then from pi to 2 pi. If we look at the integral from 0 to pi of sine x dx, we get minus cosine x evaluated from 0 to pi. So that'll be a minus cosine of pi minus a negative cosine of 0. Cosine of pi is equal to -1, so we'll have a negative -1 plus cosine of 0, which is +1. So we get an area of 2. On the negative area part, if we integrate from from pi to 2 pi, sine of x dx, We get a minus cosine, the antiderivative, evaluated from pi to 2 pi. So now we just have the same expression the other way around. We have the minus cosine of 2 pi minus a negative cosine of pi. Cosine of 2 pi is equal to 1, and cosine of pi is equal to negative 1. So the area in each of those, bumps is equal to 2. And so since one is positive, one is negative, and they're the same, when we integrate from 0 to 2 pi, we end up with a definite integral of 0. We would say that the total area is equal to 4, but the definite integral is equal to 0. Because if we're just counting area, we don't count negative area. That's just what the definite integral telling us that the antiderivative is decreasing. Any questions?
Professor Rich, I got this question on the last example. We have like interval 0 to 2 pi on the left. And then on the right, we have a negative cosine with 2 pi. Isn't it supposed to be a minus, like a big F A B minus big F A? But how come we have a plus here?
It is. It's capital F at B minus capital F at A. So here's capital F at B minus the capital F at A. The function, the antiderivative is negative, so there's the minus, a minus makes plus.
All right, got it. Thanks for me. Got it.
All right, so there's a lot going on in our definite integral stuff. We know that definite integral should tell us about the area. The fundamental theorem of calculus shows us that we can use an antiderivative to calculate that area. Since the derivative of the antiderivative is just the function that we're integrating, the sign of the function we're integrating tells us about the direction of the antiderivative. So we can combine what we know with this area business with what we had learned previously about the sign of the derivative telling us about the direction of the function. And then there's this whole antiderivative business that we have to sort out because we know very little about finding antiderivatives. Any questions?
Yes, one quick question again, Professor Rich. So on the total area, we have 2 plus 2 is 4. On the right, we have a negative 2. How do you put on that notation?
We don't count negatives when we're calculating area. Area is always a positive quantity, but the definite integral said the definite integral from pi to 2 pi is negative 2 because the function is below the x-axis. So the definite integral says that's a negative 2. We have to read that as an area of 2. So that's below the x-axis.
So in other words, the answer will be 4. Am I correct?
Yeah.
Okay, thanks.
Take the absolute value of the definite integral.
Oh, okay. All right, thanks.
But notice that if we want to find area, we can't just integrate from A to B. We have to check and make sure that the function is not both positive and negative on the interval. All right. Just a short meeting today. That's going to do it for today. I will see y'all on tomorrow. Keep working on the homework. Everybody have a good day, and thanks for playing.
Thank you.